Hey everybody, welcome. Thank you for joining us today, this beautiful Wednesday, March 30th. Today we're going to be talking a little bit about the what's and whys of induction cooking. I definitely invite you to ask as many questions as you want. We can make this a bit of a discussion. If we get some questions in the middle through the chat box, that's great. If not, you want to sit back and listen and enjoy, please do so, and we can certainly ask some of those questions later, and I'll provide my email address, so if something comes to you a little bit later on, please feel free to ask that way as well. So my name is Mark Dusler, and I am the consulting chef here at the Frontier Food Service Technology Center, and we have been working with Induction as well as other commercial kitchen appliances through testing and things like that for many years, and our focus really is on that decarbonization side. So we are fuel neutral, we're unbiased, but we do work with partners to get that message out there and help people make the most educated decisions they can possible. What I do is I bring about, well, not to date myself there, about 26 years of experience working in primarily full service kitchens, so scratch cooking, things like that. And my goal is to, really help take the data, take this information, and then translate that, make it meaningful for operators and everyday users. And what I can say is we're in a bit of a renaissance period right now. It's a pretty amazing time. There's a lot of technologies that I think can really help us solve a lot of issues we have right now. Of course, labor, food costs, all rising energy costs, and using these technologies to help, I think, mitigate some of those challenges is really critical and key. And I think it's about having an open mind. And I think it's just another part of that creative process. So without further ado, I will introduce Jennifer, and she's going to give you a few messages regarding the Alameda Power Program, and then we'll hop back into the induction side of things. Jennifer?
Hi, thank you, Chef Mark. Hi, everybody. My name is Jennifer Shen, and I am the Commercial Programs Manager at Alameda Municipal Power, known also as AMP. So I want to just provide a little bit of background about AMP and what we do here. AMP is the electric municipal division of the city of Alameda. And as of 2020, all of our energy is 100% clean, and our rates are lower than our neighboring utilities. So what that means is that when you electrify your kitchen or any other gas appliance in your commercial kitchen or your home, you will be using clean energy and reducing your greenhouse gas emissions. Chef Mark, next slide, please. So we are, oh, sorry. Let's just go through the whole slide. Thank you. Sorry, I forgot that I had animations on this one. So right now in Alameda, we have natural gas in buildings, which is 27% of our greenhouse gas, GHG, emissions. And with the city of Alameda's CARP goals, and along with AMP's own strategic plan goals, we want to reduce that greenhouse gas emission. And we are creating programs to help Alamedans electrify their businesses and their homes. Next slide, please. And before we jump back with Chef Mark, we are giving away a induction countertop range to our participants today. And so if you're interested in entering this giveaway, please enter your name, email, and zip code in the question box. And we will reach out to the winner after a few days after this webinar and arrange how to pick up your new induction range top. And back to you, Chef Mark.
First, let's look at we're gonna kind of frame this with a little bit of an agenda so you kind of know what to expect, what's coming, and I would say, use that to help frame some of the questions maybe you have. So, keep them turning. And what I would say is, as we're going through these things, I think the term think outside the box is obviously overused quite a bit. But what I would say is we're going to show you some pretty literal things, especially in the demo. But I would say use those as a way to extrapolate and think about maybe things you're doing in your own processes, and how that might apply to something you are doing. And then I would say frame that within the challenges that you're currently having or the questions that you currently have regarding your operation specifically. So if labor is a challenge or food cost is a challenge, or probably both are a challenge, or even more specifically, if scheduling is a challenge or something like that, talent management, those things can be pretty tough. So take the demonstration side of things and see if you can apply that, and maybe that'll help generate some of your questions. So first, we're going to look at just what induction cooking is. I think that's important just to give everybody a baseline, so we all understand, where we're coming from. Everybody has kind of the same information to start with, and of course, how does that work? A cook knows how and a chef knows why and all that good stuff. But I think just knowing the why helps us extrapolate so much more. And then, of course, the types of induction for commercial kitchens. We'll be looking at the common types, and we'll also be looking at some other applications of other technologies that might help complement induction. We'll look at some other ancillary benefits of induction cooking and holding, kind of bringing that whole thing back around, not just the literal energy savings of just induction, but there's actually a lot of other components that can really help out as well. And then we'll jump into that induction demonstration, and we'll do some questions and answers as well. So first off, what is induction? Well, to start with, I think it's important to say that induction has actually been around for quite a while. They started really perfecting it. Well, induction itself has been around since the dawn of time. Us harnessing and understanding and using induction has been around for maybe the last 2 centuries, I would say. We started looking at electricity and how that works and electromagnetic fields. But then really honing in, I would say, actually in the 1920s is when they really started working on that. And then Westinghouse and some other companies started looking at that from a cooking application and things like that. In the 50s, I would say, is when they really started looking at that. And that was primarily in the residential side. We didn't see a lot of it in the commercial side. But of course, as we've seen, just varying technologies become accessible. Induction has, of course, been one of those things that has been attractive, especially in markets like Asia and Europe, where energy is much more expensive. You're often trying to shoehorn in a restaurant into a very small space. You don't have a lot of you can't have a lot of heat in the space, or you don't have access to a lot of ventilation. So things like this become very attractive. So how it works is basically you're taking an electrically charged copper coil, and I have a picture of this in this next slide, and that's underneath the cooktop surface. So imagine the glass, and then there's this little disc underneath there. And what that's doing is it's generating this electromagnetic field full of these eddies and currents. And when you put ferrous metal, and ferrous metal is basically iron, anything that's magnetic, in that field, it starts interrupting that field and then exciting the molecules within the metal. So kind of think about it as, when you rub your hands together, that friction makes heat. Well, if you do that in a very intense fashion, then it makes the pan hot. So the vessel itself is actually what's creating the heat. It's the excitement of the molecules in the pan itself. So it becomes your heat generator. Now, without the cookware there, what's interesting is that field, without the ferrous metal in that field, the unit is not consuming any power. Now, it might be consuming some power just to run the unit itself, but it's not actually consuming any power. Like, there's no power going, just out into the ether, right? Like we would think of if we think of a gas range or electric resistance ranges. So here's a picture of what those units look like taken apart. This is a commercial unit here. And you can see that copper disc, and then around that you can see there's a few different components. There's heat sinks. We have electronics inside there, which are actually really, really important. We're going to talk about the importance of that as we move along. And then on the other side there is we basically just took that shell off in its complete form, and you can see what it looks like if we just kind of an exploded view. So there's 4 critical components, internal components. One, we have those electronics like we were talking about. And that software has a lot to do with the sensitivity of the unit and how well it's going to regulate temperature. One of the neat things about induction is you can actually cook by power or by temperature. And it's able to do that by that thermistor. The thermistor is essentially a temperature sensor. So what it's doing is that thermistor touches the top of the glass. And what it's doing is it's getting feedback from the temperature of the glass. And then through that software and the electronics, it's taking that and then offsetting certain kind of temperature. And it can actually get pretty close. I mean, it's not going to be an immersion circulator close, but you can get within a few degrees of your set temperature. And then of course cooling. I think that's a really, really important thing to talk about here. Is I think a lot of times people think of induction units as breaking because the glass breaks, right? Because it's glass and it's supposed to break. But what we find most often is the units actually fail because they're not able to cool. Think of your computer at home or your laptop. You hear those fans kicking on. Heat is kind of the enemy of electronics. So the more we can keep them cool, the longer they'll last, less stress they'll be. And on the outside, of course, we do have that ceramic glass top, like we were just talking about. the cooking zone, you'll see oftentimes they'll be outlined in a very distinctive way. And the reason for that is because induction is very focused. It's a focused field. It's basically coming straight off of wherever you see that circle. That's where you're going to be seeing it. So if you actually put a pan halfway on the induction unit, halfway off, you'll actually see like a ring of where the heat is being applied to the pan, because where the pan is heating up, because it's just going to be within that magnetic field. And then down below there, you have controls. We have varying types of controls, which we'll go through here with some of the units we have. But on this one, you have push button. You can choose to either cook by temperature or by power, and then you have your display, which is obviously telling you, what you're doing, what your set point is, or what your power setting is. So this is a great illustration of how tough that glass can be. Typically it's a glass ceramic surface, and what they're doing there is dropping a bowling ball, obviously pretty impressive. Here we see the removal of the pan and how the unit actually shuts off, right? So because the pan is generating the heat, and if that electromagnetic field is basically not generating anything, the unit knows that, and then it can just shut itself off. The other nice part about that is it has an overload protection in it. So if somebody leaves a pan on there and it's cranked all the way to high, and it sees that temperature goes up too fast and stays there for too long, it'll actually shut itself off, which is a great safety feature. One thing to know about pans, there's often a question of, are my pans going to work with induction? How do I check that? A great way to do that is, one, either look at the packaging, or the pan itself will sometimes have that induction logo on there telling you that it is induction ready, or by a magnet, right? Because it's a ferrous metal, so therefore it's magnetic. So the stronger that magnet sticks to it, the better it's going to be. The good news is the most expensive pans aren't always the best pans to use with induction. Often cast iron is actually going to be your best because it has the most iron content in it. People ask about Le Creuset pots or Staub. If those are typically cast iron enameled pans, so they work pretty well. As long as the pan has some type of ferrous metal in it, or is clad with that metal in the bottom, is basically what's happening, because stainless in and of itself is not usually going to be that great of a performer. But what they'll do is they'll actually create the pan in such a way where it will perform pretty well. So how does induction differ from conventional electric range tops? Well, and when we're talking about electric range tops, we're talking about either, you may have heard of like electric resistance or speed coils, things like that. So traditional range tops use resistive elements, right? Think about it as, think about like a light bulb. It's kind of the same thing, right? You're using resistance to generate heat energy. It's dissipating out, and then it actually has to conduct into that pot. So you have to transfer this energy that's been generating in the coil into the pot, and then the pot has to transfer that into whatever it is that you're cooking. So, the more layers, you have to pass through, it's going to be less efficient. And then there's some other pieces that we want to talk about there too. One of those is that because it's going through conduction, you can have issues where in the very beginning, we often see that the electric resistance ranges are pretty efficient. But what happens is over time, because of that conduction, you start to have either warping of the coils, or you have warping of the pans, and that equals less surface area. Less surface area equals, less efficient transfer of heat. And now you just have a whole bunch of problems where these things just get slower and slower, and they're just not as reactive as we'd like, or I'm sorry, they're not as efficient as we'd like them to be. And then the other issue, of course, I think we've all experienced, if you've used an electric resistance range, is it's not very responsive, right? If we turn it up, it takes a while for it to hit its set point temperature. Oftentimes it overshoots or exceeds that. And then if we want to turn it down, it takes a long time for the coil to cool down. Often we have to like remove pots, let it cool down, put them back on. So it's very cumbersome. Not always like the best option if you're, doing a lot of saute work or things like that, or you want, stable temperatures. Here we're looking at, kind of a comparison or side by side when we're talking about gas versus induction. So you can see on the induction side, it's a very, very uniform, field, right? And it's really just encompassing the bottom of the pot. And that heat then travels into the water or whatever it is you're cooking, and a little bit up the sides, right? But really what you're getting, most of that heat, even on the sides, is just from the water or whatever it is you're cooking touching the sides, not so much from the convective properties of gas. So gas is even more inefficient, I would say, than electricity. It is. We'll show some graphs there, but I'm saying more efficient in the sense of your heat up time and then your cool down times. And the reason is because it takes so much energy. it takes so much energy to transfer that heat, or you're getting so little of that heat into the pot because so much of it is just dissipated out the sides, right? So you can see it kind of billowing out the sides, and it's just not very effective. We have some pretty cool imaging that we've used with FLIR software I'll show you in a second that kind of illustrates that point. So as far as fast heat up goes, the induction hob, of course, very, very quick. The gas burner, pretty quick and pretty responsive. The electric element, not so much, because we're going to take into account when you start getting that warpage, which does happen relatively quick. Quick temperature response, of course, we know that when we turn gas up and down, that temperature is going to change pretty quickly. Induction is actually the same way. It behaves more like gas than it would electric resistance. An electric element, as we just discussed, does not do that, right? It's slow to heat up, slow to cool down. And so what that does is, if we're looking at these for primary candidates for something like saute, something where we do need to change that temperature quite a bit, we're not seeing that as much with the electric element, whereas the gas and the induction, we certainly do see that from a performance aspect. So to summarize that, induction works by heating the pan. Induction cooking requires a magnetic pan. There are some pans out there, some technologies that are using aluminum, or they can heat up copper and aluminum, but they're very, very expensive, and I don't know that it's really worth it. One of the upsides too to using, stainless steel or steel pans is they're just much more durable too. They're also a little bit safer. The problem with aluminum is that the temperature swing becomes really, really high, so you have to overshoot quite a bit to be able to do the work you want to do, because basically the food just saps all the energy out of the pan. So you have to really, really get it really hot to be able to achieve, say, the same thing as you would have to do with a cast iron or a steel pan, where it's able to retain a little bit more of that energy, so you don't have to have such wild temperature swings. And at the end of the day, it's just going to be cheaper anyway, because in the long run, if you're not having to replace pans as often due to warpage or things like that, it's just overall better investment for the long term. And the cooktop is made of a very hard ceramic glass, right? So durability. I would say when you're choosing them, it is important to note that just like anything else, there is light duty, medium duty, and heavy duty. So if you're using a light duty, even gas range or electric resistance or induction, and you're in a heavy duty application, you're going to have problems. It's going to break because this is not intended for that. So when you are looking at different units, it is important to ask that question. What duty is this? Is it going to fit the needs of my operation? And of course, induction is just as fast, actually faster, and just as responsive as a gas range would be. So we're looking at the nuts and bolts, the energy efficiency and energy costs. What I like to start with here, because I like to come at this from an operator's perspective, is that energy efficiency, there's a correlation between energy efficiency and performance. And what do I say when I say performance? Well, we define energy efficiency for this application as the amount of energy that the appliance consumes that actually makes it to the food. So what does that equate to? That equates to faster cook times, less heat to my space, which we'll talk about a little bit more, and often just that means that what that means is I can potentially cook more and make more money, right? If we should always be designing for success, so we should always be trying to maximize our revenue potential. So here's a graph of the typical range top efficiencies. And what you'll see there on the left-hand side, or the gas hot top, is pretty surprising. And what we find is your gas hot top, which would be like a French top, or your gas open burner ranges, is regardless if it's the most high-end or the cheapest or your house or commercial, they're usually topping out around 35%. So what I like to do is I like to think about that in pennies, right? It's a much simpler way of thinking about 100% is 100 pennies. So 35% means 35 cents of the dollar I just spent is actually going to my food. It's going to my pan and then into my food. Everything else, it's either going out my hood or it's making my space hotter, which now I have to pay to cool that down too. And then we have gas-powered burners. One of the issues with gas-powered burners, yes, the efficiency is better, but they're very sensitive. So if food starts falling on them, we start to see a decrease in their performance pretty quickly. They're more high performance, so therefore they require a little bit more maintenance. And it's not always clear that the ends justify the means in that situation. But of course, they are out there, so we wanted to test them as well. And then we have our electric hot tops. You think of that as like your ceramic flat tops. It's still resistance or infrared coils down below, and then it's actually transferring to the glass. So it looks like induction, but it's not necessarily the same thing. And then our electric resistance elements, which we just discussed, the coil or a speed coil. A speed coil is essentially the same thing. It's a coil, and then it has like a metal cover over it, if you want to think about it like that. And and that's just to protect the coils from getting all gunked up and things like that. But it actually also decreases some of that efficiency because now you have just another layer to transfer that energy through. And then finally, we have our induction hob. And I think it's important to note there that our induction hobs are about 85% efficient. So if you're looking at that from, if we're taking it from the lowest there, we'll say the gas open burner, because that's probably what most people are going to be using, at that 35% level. And then we're looking at the induction hobs at that 85% level. We're looking at those pennies. I mean, 15 cents is a lot easier to swallow than I think 65 cents. So, and then of course, there's all those other benefits, which we'll talk about here in a second. Efficiency. So where does that heat go? This is a really great image. This is a FLIR image. And what you can see there with the induction side, that 85%, what does that mean? Well, it means that all that energy is actually getting transferred into, in this case, we're using water. Why do we use water? Well, water actually requires a lot of energy to raise in temperature or decrease in temperature if you're talking about refrigeration. So the point being is that water is actually just very, very intense. It requires a lot of energy to do that. And it's also very stable. We can measure it. We can use the same amount of water, so it makes it very easy for comparison. So when we're looking at that from the induction to the gas side, you can see that all that convective heat, right? Where is all that heat kind of concentrated? Well, it's mostly at the bottom, but it's very dissipated, right? And then you can see it kind of rising over the sides of the pot and then, out into the space. Whereas if we're looking at the induction picture, you can see, yes, it is very intense at the bottom, but it's very focused, and all that heat is actually being generated by the pan. And what you see there is that orange layer is essentially, that's the water inside actually meeting temperature. And then, of course, you see some of that vapor coming off the top, but that vapor is much hotter, of course, than what we're seeing with the gas range. So one thing to consider, though, right, we always want to be looking at all angles, is that CapEx versus OpEx. And what we find is, of course, your gas ranges are going to have a lower capital cost. They've been around for a long time. The components are much more simple. They are very durable. Excuse me. And your induction ranges are going to be 2 to 4 times, higher in cost. What I would say, though, is in food service, it's important to realize that we have not always been very good at amortizing or spreading out our costs to do business and versus our revenue potential. Who has been good at those types of things, if you need proof that it exists, would be to look at your major chains, right? A lot of major chains figured out a long time ago. Now, granted, they have the capital and the resources, but why should we all not capitalize off of their efforts? They realized a long time ago that loss in revenue will eclipse upfront costs. So what do I mean by that? What I'm saying is, if this thing cost me $4,000 and this one cost me $2,000, but I'm turning away, $1,500 a day in revenue that I can't capture because people just aren't going to, I just can't get there. It's a bottleneck. It doesn't equate very well. Now, of course, that's a very perfect way of looking at it. We know that food service can be a little bit messy, but I think if you're always designing for success and you do have kind of an idea of, what your other bottlenecks are, and if this is a major one, it might be a little bit easier to justify those costs if you're thinking about it in those terms. So yeah, 35% versus 85% efficient. So the energy bill is actually equal. We brought that up kind of towards the end there because it's a little bit surprising in that most of the time in California, while electric appliances are actually much more efficient typically than gas appliances, and that's because usually you're going to have a heat exchanger. You have to move. You have to transfer the energy into whatever it is that the medium that you're cooking in, whether it be an oven or a fryer. You heat the oil, and then the oil heats the French fries or whatever it is. You're just getting some. There's loss in efficiency there, whereas oftentimes with electric, it's much more efficient, out of the wall because, the elements are directly inside the oil, having to transfer the energy. However, where we see a problem with that currently, which we're seeing this change, is gas is a little bit cheaper just to send down the pipe, right? You put one of gas in the pipe, you get one of gas out of the pipe. And for a long time, I was raised on gas myself, and it's been very refreshing to use induction and electric technologies because they weren't always available. But what I can say is and I think they kind of had there's a lot of myths around them, and I think that it's important to dispel those myths. But what we're talking about here is because of the inefficiency of the gas range, that 35% versus the 85%, we can run calculations because we make these tests comparative. We actually find that the induction is basically even with the gas range, if not sometimes actually cheaper. And that's because, you know, there's all these things we have to think about. When I remove the pan, it's not using energy. If I leave my burners on, it's going to be constantly using energy with my gas, even if I'm not using that burner at that moment. So this is not true for most electric appliances like we just discussed. So to summarize, induction uses energy more effectively than gas, right? Induction cooktops have a higher capital expense. So it is important to pencil that out. Make sure you understand what you're doing, why you're doing it, and of course we can help you with that. And induction has about the same operating cost as gas, and that's due to that inefficiency. So some of our non-energy benefits, and that's kind of what you know, I kept alluding to. We'll have some slides about these later on. I like to break it down based on, you know, what are our challenges in an operation in a kitchen. And of course, safety is a big one, right? It's kind of the weird one that we never really want to pay attention to. We never, you know, it's like paying for insurance, you know. Insurance is always expensive until you need it, and as long as it's good insurance, you're definitely glad you had it. And safety is very much that same. I think it's a part of the same family, right? You never really like want to think about it. It's kind of the boring thing until something happens. But if something never happened, it's fine. But that's part of just maintaining that culture. Precision has more to do with you know, food costs, yield percentages, and things like that. And what I would say is, of course, they're all interrelated. But you know, by looking at these different technologies and understanding how they work together, they all kind of feed into each other. So, you know, if my yields are better and my food costs are better and I can take less deliveries, that means I can, you know, pare down my production schedules and make things much simpler. You know, food service is about making constants out of variables, and precision is a critical piece to that. And then leading, of course, right into that is the labor. You know, safety and precision feed right into that labor. How much labor do I need to accomplish certain tasks? Of course, the more labor I apply, the less my margin is for revenue potential. Because I have to just keep spending that money on doing laborious things like putting away more orders or whatever that might be. More people equals more chance of people getting hurt. So we want to look at all of these aspects and how they're all interrelated. So here's a good example of how induction can reduce that fire and burn risk. Here we have some mushrooms cooking in some butter and oil, which is clearly pretty hot. What you see there with the napkin is there's no scorching like you would see with electric resistance or your gas ranges, and it can actually touch the surface, and it's not that hot. Now, of course, it's going to be hot because you're going to have heat transfer back in, you know, from the pan into the glass. But what I can tell you is it's going to be nowhere near the same temperature as if you touch electric resistance coils or even the grates on a gas range. Here's kind of just a little illustration of an example of how the induction ranges can be used in various ways, because they have that feedback technology. And this is to illustrate it has a little bit of a probe on it, which gives it even more feedback. And I actually have that unit behind me. We're going to use it today. It allows you to free up some of that labor. It also helps with your food costs, right? If we're doing things like stocks or things that require reduction in volume, one of the challenges you have if you're using a gas range or electric resistance is that volume decreases. It requires less amount of energy to, you know, maintain that temperature. So then what happens is the volume goes down, the temperature goes up, and then what we have is issues with boiling, and it's just not a controlled situation. Excuse me. And so what that requires now is that requires a cook to be monitoring that process, and it also increases the chances for somebody accidentally bumping the gas valve or whatever, or forgetting things like that. But it also ties up more of your labor. Well, if we can have things working in the background, our machines working for us while we do other things, I think there's two important aspects there. One is that we're actually freeing ourselves up to be more creative because we can do other things, but we're also freeing up our cooks to do other things, right? So now that cook can just get that much more done, or be that much more prepared for service, or be able to prep that much more. And again, we're looking at that revenue potential, that bottleneck. It's not just literally the CapEx versus the OpEx. There's a lot of other components that go along with that. And then, of course, you know, easy to clean is really, really critical. I worked with a chef, and he put induction in, and along with some other really great, efficient pieces of equipment. And that translated to his cooks being able to break down in about 45 minutes to an hour. That includes wrapping up, cleaning up the kitchen. And he was spending about $900 a month for his night cleaners. And basically the night cleaners were just cleaning the floors. So they were able to do all of this work because it wasn't that hard to clean it. You just wipe it down. You can move them out of the way. They're much lighter than their electric resistance or range brethren. So it allows for you to be able to move these things out of the way, clean up quickly, put them back, and you're at a ready state for the next day. So to summarize, right, no flame means less fire and burn risk. That could also translate to potentially lower, workman's comp premiums, things like that, right? If you have less risk, less hazards, you should be paying less in your insurance. I can't guarantee that, but it is certainly something worth looking at. And you can also thank the chains for that too, right? Because to scale, they go out there and they want to try and get the best deal possible. So they are often asking their insurance companies, hey, we're doing these things. Is there something I can get for that? Precise controls, right, can reduce that labor and food waste. And then, of course, easy cleaning also reduces labor. And it also extends the life of the equipment as well. So let's look at a few different types of induction equipment. I'm going to go through a few pictures here first, and then we're actually going to look at some of those pieces. And then what we'll do is we'll take that, we'll step into the kitchen a little bit and see how they work. And if you have any questions, we can address some of those questions as well. So here we have some tabletop models. The cool thing about the tabletop models is you can see the configurations can be varying, right? We have 120 volt all the way up to 208. You can have the units, side by side. You can have them lengthwise. So, depending on how you're using them, you can change that configuration. And again, they're light. So if you want to move them a certain way or move them over, it is a really advantageous way to keep your kitchen modular, that fast, small, flexible kitchen. It is important to note, I know this will come up, and that is ventilation, right? So it can be a little bit misleading because you see that like the unit in the top left by the tabletop low, or the title there, that unit can be 5,000 watts, right? So 5,000 watts is the equivalent of 80,000 BTU for a stove. That's a pretty small package for so much power. Now, ventilation is still in question there because of the potential of the piece of equipment, right? If it can fry and it can steam and it can do all of these things, you still need to have ventilation to get rid of that water vapor or the grease, things like that. So while there are some ventilation options there, with the 120 volt units and things like that, typically if you're going to be using these in a heavy duty fashion, you still will need to have ventilation. And I know that people will ask probably more detailed questions, and I certainly invite that. There's drop-in units. So these would be placed in either a table or a countertop or something like that. They're really great, like really nice fit and finish. Again, you're going to be trading a little bit of that modular functionality, right, of the kitchen. You're kind of stuck with what you got. However, if that works, if you have an island or something like that, or a suite, then these are a great way to go. And as you can see there, you can even have drop-in wok units. So stock pot ranges, you're stepping up an even higher wattage, right? So to step back there, the wattage kind of, there's a, wattage and voltage and amperage are all interrelated, and then you can get into different phases and how they're basically, getting higher amperage over multiple circuits. But the reason we want to bring that up is the amperage is really what you're talking about here in the sense of how intense that magnetic field will be. The more intense the field, the more power that the unit has. The hotter it gets, the faster it'll heat up. So that's when you're talking about that wattage. We usually just talk about it in those terms. That's what you're talking about. So if I say that stock pot range is 7,500 watts or 7.5 kW, 7.5 thousand watts. That's what we're talking about. We're talking about like what its potential is as far as being able to heat up large amounts of something. So in this case, or how fast it can heat up, which we'll talk about a little bit more with woks, because that's all about recovery. And then of course we have our standalone units here. We see some standalone woks, range tops, like you kind of think of more as a traditional range top. And as you can see there, these primarily have the controls we'd be looking at if we were going to be doing a lot of saute work, right? We'd have dials and knobs and things like that. Here's just a couple of cool pictures our director of education took when he was at the Hotel X conference. And this is a full induction line. As you can see there, the neat thing about it is they are very clean, right? It's a very nice looking line. It's very simple. As you can see where it is easy to clean. One thing you will notice, and we'll talk about this with the other units, is you'll notice there's 4 hobs versus 6 typically you'd find on a gas range top. Now that really might not be too much of an issue in the sense that if you're able to cook faster, and I think you'll see what I'm talking about when we go over to the range top, it's actually a lot faster. So you'll see that throughput may be okay. And then we'll also look at, there are just a few other technologies that maybe you should consider instead of just taking this one-for-one approach of, gas range to induction. Here's a full-size wok station. Now we put this in here, and we actually have one here of the same unit here. I'll show it to you in just a minute. And the reason we brought this in is because it is important to note that Western style woks aren't very conducive to traditional wok style cooking. And that's because you use both hands typically when you're doing traditional wok style cooking to hold your tools. So what you're typically doing is either with your foot or your knee or some part of your leg, you're controlling that power setting. And with these here, we can actually control that power setting, as you can see there with those knobs on the bottom. And then of course, induction warming and holding. I think this one is often overlooked, but I think is a really, really important component. And we'll discuss why here in a few minutes. But in the first thing, the most obvious thing would be just how much less energy it requires to do the same amount of work. So if you're looking at wet wells, which we're doing a lot of work right now, actually examining wet or dry holding wells versus induction wells, the energy usage is pretty impressive. You can kind of think of the wet wells and the dry wells as being a little bit dumb compared to the induction, because the induction has that feedback. It's able to modulate temperature much more accurately. Therefore, it's modulating its energy use. And then, of course, there's some other capabilities such as retherming and just the weight of them. You can move them around much easier, which we'll talk about right here. So I think what we'll do is, before we hit that last part, we'll look at some pieces here, and then I'll kind of wrap it up with that little part. We'll keep that as a mystery for the very end there before we step into the kitchen. So over here, we have some examples of some holding equipment. And what I'm going to do is kind of move through, we're talking about that wattage or that intensity. So we're going to kind of step back and go in a little bit reverse here. We're going to go from the least intensity to the most intensity, at least for what we have in the room. And over here, we have a few different examples of holding technologies. One, we have, you can see some of this, but it's essentially a buffet, right? It's what you think of as if you went to a buffet style setup, and you would be wanting to take food out. What you have in here are these little hobs that sit inside here. They're designed to accept 2 pans essentially. So what you can do is you can have 2 half pans in here or 1 full pan. And then down here you have the controls. The cool thing about it is you can actually set that control by temperature. So I can control the various temperatures depending on what I'm putting in there. And rather than being like a number system of power, like 1 through 10 or 6 or whatever the dials say, I can actually control that pretty accurately by temperature. So I can say I want it to be held at 180 degrees, and it'll be pretty close to that temperature. Certainly much closer, I think, than you're going to get with most of your just dial-based dry and wet wells. These are pretty neat. This is just a warmer in and of itself. So I put a pot on here because I think from a back of the house perspective, this is actually pretty cool. You can put it away when you don't need it, bring it out when you do. A lot of times we have double boiler, or I'm sorry, water baths or things like that on our lines to be able to hold hot items, and they're taking up either range, griddle space. Whereas with this, it's only 120 volts. You can usually get a few of them on one circuit, depending on what else you have on that circuit. And it's very, very simple. It doesn't go by temperature. It just has like 1 through 5 power setting. But the idea here is that you have something that's just very simple to put out, excuse me, and pretty accurate, very low profile. And I can now use this space for prep or production, or maybe I don't want to run this dish right now. I can put that away and reuse that space. So a really great way to kind of harness that technology and make it versatile. Here we have a soup well, and it's just kind of as it sounds like it. It's designed to primarily hold liquids, soups, chilies, things like that. What's really neat about these is they're actually designed to retherm. So rather than transferring, I take soup out of the walk-in or whatever liquid it is, I put it on the stove or whatever, heat it up, and then I transfer it once it's at temperature into the bane and then hold it there. This will actually heat that up for me. It has a little program on there. You can put soup, chili, excuse me, and from there it'll actually even tell the cooks to stir it, time it, and tell you how long it's been in the well and alert you. The other neat thing about them, you'll notice on this unit actually has one in the bottom too, but you'll see it has these they're basically like little pressure sensors. And what that's doing is, as the weight, as the volume decreases in the pan and the weight gets lighter and that button moves up, it's telling the unit that there's less stuff in there, and it'll actually decrease its temperature as it moves down the inside of the jacket, or even it'll just decrease temperature here inside this pan, and then that prevents it from getting that crustiness or that burned, those burned issues that we would have if you just have like a dry or a wet well. Over here, what we have is kind of two different kinds of standalone ranges, and then we have like a more robust like oven range combo. Here in the standalone, what you'll see is we actually have push buttons. So when you're deciding on the type of unit you want to use, it is important to really think about those controls. Now, this probably wouldn't be very conducive to a lot of saute work, because it's just not, you're not going to be pressing a lot of buttons. You want to be able to move quickly. It's not as exact as, say, like if you're doing a lot of pastry work or a lot of production work. Production work, this would be really ideal for, because I can set by power or by temperature. I can put timers on them, things like that. So a lot more functionality in that way. Here we would see on these two, we would see that it's much more like we would think of as a traditional range, right? I have a dial, I can turn that dial, and what I'm doing there is just same thing. I'm adjusting power setting. There's a little indicator typically on most of them on the range top itself telling you that the unit is on. And this is usually where I like to bring up, the whole like comparison of gas versus induction. Well, it just doesn't seem like it's a natural thing for me to use. Well, what I can say is that is true in the beginning, but what happens is you get used to it, and that's due to all the attributes of induction. Primarily, it's stability. So in the beginning, when we use gas, we're looking at that flame. That's our feedback. As a cook, you're constantly looking at that flame, or just glancing at it really, and just over time you get used to adjusting it and using it. And what we actually end up doing a lot of times is we actually overshoot temperature. We have naturally overcome the challenge of the inefficiency of the gas range. So if I'm a saute cook and an order comes in, typically the first thing I'll do for most dishes, not always, I'm going to start heating up this pan while I go get whatever it is I'm going to cook. And I'm actually going to intentionally overshoot temperature, because whenever I put something in here, the ingredient is going to sap the heat out of the pan. So I'll put this on high or whatever it is appropriate to do the process. I'll go over, get the ingredients, and then start the process, and I'll either leave it on high, or I'll reduce temperature immediately to kind of like get it into that sweet spot. Well, with induction, you don't really have to do that. What ends up happening, I think a lot of times in the beginning, people are worried that induction's too slow. It's actually the opposite. It's really fast. It heats up much quicker, but it's also very stable. So from a saute perspective, what you end up doing is, because a lot of time, even in saute work, you're doing the same processes over and over again. They might have slight variations, but it's like going to be essentially the same 6 processes. So what you'll do is you'll put your pan down, and rather than overshooting, you're actually going to probably start putting it closer to the temperature you actually want. You put your ingredients in and you leave it, because its recovery is really fast. So it becomes much easier. And by having these 4 hobs, it might actually equal your 6 hobs, because you're able to get that much more work done, because you're not having to constantly fidget with it. It requires less active work. And as we all know, that's why mise en place is so important. Is what we're trying to do is eliminate active thinking so we can focus on the things that we're doing. Over here, we have some woks. I'll step on this side here. And the reason we bring these out is because they can be misleading in the sense that they're actually very, very powerful. So this is 5,000 watts, which is equivalent of, I believe, about 90,000 BTU right in there, maybe 110,000 BTU, depending on the type of pan you're using, right? We're saying that the efficiency matters. But why that's important is because in woks, you're basically making this one pan meal. You might be doing 3 or 4 different processes using the same pan. In the beginning, maybe we're going to deep fry. We're going to take that oil out. We're going to then put in some water and blanch or steam. We're doing something like that. We're going to take that out, and then we're going to shallow fry at the end, and then maybe combine all the ingredients. Well, what we're doing there is we're constantly sapping the energy and changing the temperature of the pan. So what's really critical there is to be able to get that pan back up to the temperature that we need to be able to start doing that work. Well, because of the efficiency of the wok, because of the efficiency of the induction, the wok is much more responsive to those temperatures. And then, of course, as you step up in production, or you step up in that intensity of your operation, you'd go to much more intense versions of that. So this here is 5,000 or 5 kW. This here is 12 kW. So much more powerful. And what that translates to is, essentially the same thing as far as performance goes. But I would say you kind of think of it as, this is your 5 kW ability to work here, and this is your 12 kW ability to work here. That surface area is just that much greater. It doesn't necessarily mean that you're going to, yeah, if you pour water, the same amount of water in both of these, this one's going to boil a lot faster, right? But really what that means is you can just put more water in here and get them to the same point, right? So you're able to do more work. So, let me get my little controller here. I'm going to step back over to center here just for a second, and we'll talk about. I want to talk about how the induction. There's some other considerations there, and we'll show these pieces of equipment. I kind of tripped up. My producer extraordinaire, Michael Cars, he does a great job, and then I even is great at adapting when I decide to change something on the fly. So, now talking about all the induction pieces, I do want to say that there are some other considerations there, right? There's a slight misperception that creating all electric kitchens requires all induction kitchens. It's not a silver bullet, and we do need to consider that there are these other technologies, and we should be embracing them, or at least considering them when we are, retrofitting our kitchens or building new kitchens or whatever that might be. So it's just one way of transferring that heat, and it works well for range tops. That doesn't always necessarily mean that range tops are the only thing that. Can you click my screen really quick? Range tops are the only way we want to do that. Just because that's how it worked well with the gas range top, and it'll work well with the induction range top, it might not be the answer we need. We might be wanting to look at process changes. The one main driver for that is panel size, right? I mean, panel size is something we definitely need to consider when we're building out our kitchens. And if we're, induction is a very intense process. It's very efficient, it's very fast, but it is very intense. And if we can find other ways of doing those processes in a less intense manner and just as accurate or more conducive to the specific process that we're doing, we should certainly be looking at those as possibilities. So some examples we'd be thinking of would be things like broilers, fryers, pasta cookers, convection ovens, steamers, kettles, things like that. So what we want to do is we want to say, it's not all created equal, and induction doesn't really work well when applied to these specific appliances. Sometimes just an electric resistance works just fine. So, hold on, I'm going to actually switch back over there. Sorry, Michael. And I want to show just a few pieces we have in the space and talk about that. So here we have a ventless griddle. The reason I brought this out is it's many things all rolled into one. Pretty neat. A lot of teppanyaki places and things like that have been interested in using something like this. And it's exactly as it sounds like. This is actually the working side. So the cook would stand on this side, and this would be really your customer-facing side. And what you have here is you have your ventilation system here. So it's like a downdraft unit. As the food is cooking, the vapor or whatever it is, the grease gets sucked into here, and there's a whole filtration system inside the unit that will actually get rid of the grease and the water vapor and all of those things. Now, the one thing you do have to consider when you're using something like this, or the next piece we're talking about, is of course heat gain, right? No matter what, that heat is still in the space. So however you can dissipate that heat, that might be through more efficient equipment, the temperature that you're actually running the unit at. And then, of course, you might have to use air conditioning or condition that space in some way to be able to offset that heat. The other nice thing about this is you also have your fire suppression here. So it's all self-contained. It does make it much easier. You can roll this thing around and essentially use it wherever you need to. Over here, we have what's called the plexor. And what makes this unique is some of you may or may not be familiar with high-speed technologies. And what this is kind of taking high-speed technology. So think of it as it's microwave and impingement, or high-velocity hot air, all rolled into one. And what you're doing there is you're basically heating the inside of something and the outside of something at the same time. So that outside is your texture. The inside is actually being able to heat the internal, the goods of it. Think of it, if it's a panini or a sandwich, you can actually heat the meat and melt the cheese. While on the outside, you're making that bread crispy. You can do pizzas in there, all kinds of things. What you have here is 3 different drawers. And you create your recipes here. What I would say is in the beginning, it seems a little bit difficult, but it actually becomes quite intuitive over time. And what you find too is that they all kind of like roll together. So a lot of sandwiches will behave the same. A lot of pizzas will behave the same. You might be making minor adjustments, but it's not really that difficult once you get used to it. But the nice thing here is that you start that process, it'll do its work, it comes back out, it's ready. And really what you're doing is, if your application is a lot of like front of house work or a cafe or something like that, this alleviates, or ghost kitchens or things like that, this alleviates a lot of that labor, and it also allows you to do more of that just-in-time finishing or cooking. And you can scale it really well. The other nice thing, what makes these unique, is that a lot of times high-speed ovens are using a 30-amp plug, right, for each one. So if you go to like a lot of the big chain coffee shops, they run 2 high-speed ovens. You see them in the back there, where they're making their sandwiches or egg bites or whatever that is. They typically have 2. Now each one of those units requires a 30-amp plug. Well, this for all 3 drawers requires only a 50-amp single plug. So you're actually able to decrease that and be able to increase your capacity. And then finally, there's a few different companies that make things like this, but what's really neat about this is these are braising pans. This is the smallest they make, but what's really critical about this is the functionality and the versatility. So they've incorporated things like probes. So now the unit has feedback. You can build recipes inside the unit. You can auto measure your water. So rather than having to bring buckets of water over, you just say, I want 4 gallons of water. It'll pre-measure that 4 gallons. It'll pre-sear. You can stage your recipes. They tilt, so you can get all this stuff out. Cleaning is much faster. You can do you can attach baskets to them, and these actually are on actuators, so they'll raise and lower. You can cook pastas. You can even use them as fryers if you want. They have drains in them. So really what you're looking at here is kind of like, what can I do to help save labor, scale up my kitchen production, and just be able to achieve as much as I can with the smallest space as I can. So just a few considerations there. So to summarize, what we're looking at here is, many well-developed equipment choices are out there, right? We should really be looking at all of the options we have available. What I would say is it can be a little bit overwhelming in the beginning to like try and take all this in. My suggestion is, excuse me, is to work backwards, right? Actually, if you already have your concept and let's say you're up and running, or even as you're developing your concept, I'd say define your standard. Define what is that customer experience. What are all the things that I want them to have? If it's delivery, I want them to have X quality experience and to be delivered in X amount of time, or whatever that might be. Or if you're in-person dining, have your standards defined for that. And then from there, work backwards. Say, okay, well, what do I need that's going to help me achieve these things, right? That's how you design yourself for success. As long as you maintain that initial standard, and I would say don't deviate from it. But I mean, of course, this is reality, and maybe you have to trade something for something else. But as long as you keep your core values and you start looking at and you examine these technologies in that fashion, it makes it a little bit easier to digest. In induction, of course, I think we always think of it as just cooking, but it does include hot food holding. And not all electric cooking needs to be induction. Well, induction is an incredible technology, but it's just one piece of the puzzle. We should be looking at all of these pieces. So finally here, I think, kind of to roll that all together, we're thinking about, all these ancillary benefits. It can all be really kind of distilled down into induction and kitchen comfort, right? If the cooks are happy, if the staff is happy, then that means that you're going to just make better food. You're going to make better products. But that also means that, if the kitchen's hot, that means that's just energy that you essentially bought that didn't make it to your food. And that can have all different kinds of effects, whether that means longer cook times, less consistent product, and unhappy staff. So can induction cooktops help reduce kitchen ventilation requirements? Well, yes, in theory they can if they're consuming less energy or dissipating less energy into the space. Again, it does depend on the type of process that you're doing. So here we just have a few different examples. Again, we use our boil tests to show this, but we're looking at that exhaust hood capture and containment rates. And so what we can see here from the gas range top is it's considerably higher than the electric resistance or the induction. It is important to note too that if you are using gas, you do have to have a hood, right? Because if you don't, everybody's going to go to sleep and your production's really going to go down, and then they'll all die too. So that's not good. We definitely want to have ventilation in those situations. But with the electric resistance and the induction, we obviously eliminated the carbon monoxide problem. But we still do have to look at how much heat and water vapor and potentially grease we're putting into the space, and then your ventilation rates are adjusted accordingly. So as you can see, though, the decrease is pretty good. And because of the electric resistance and the induction as far as capture and containment go, they're going to be about equal. So there you go. It's about 1,000 CFM more than induction on average. And what does that mean, right? So just to kind of put that in perspective, if you're moving 1,000 more cubic feet per minute, that means that, well, the ambient temperature of a room is not because of the air inside the room. It's because of the solid objects, right? It's all the things in this room actually make it this temperature. As long as they're all at a stable temperature, the room stays at a stable temperature. Well, the more air we move through the space, the more, think about like refrigeration is moving heat through the space, or if we're radiating out more heat than the air conditioning can remove, that temperature is going to slowly or quickly rise. So if we can keep the CFM down and we're able to use the conditioning systems as they're intended to be used, it actually creates a more comfortable kitchen. So here we just have kind of an idea of how that heat is traveling around the space. We have conduction, right? It's that heat coming right up to the meat. It's going from the flame to the grate to the meat or whatever it is you're cooking. We have that radiation heat, that heat that you feel on your face when you're right in front of something that's hot. And then of course that convective heat, think of it as like, it's blowing up, it's moving up because it's hot air is rising and it's sucking air and moving. So these three can affect, how that's one, the quality of your cooking, but it can also affect, just that kitchen space in general. So the takeaway there is induction range tops generate less radiant heat, right, than the gas range tops for all the reasons we just talked about, right? There's less convective heat. It's the vessel itself that's actually heating, so it's going right to the food. And then from that, we're potentially making the kitchen much more comfortable, and we're saving energy on air conditioning and allowing the air conditioning that we are using to be much more effective. So to summarize there, induction can reduce that kitchen ventilation costs and increase kitchen comfort. Okay, so now we're going to be doing some live cooking. I have a few different pieces here that we'll talk about. I'll go over the pieces first, and then from there we'll go through some of that live cooking. I've been on kind of a Latin kick lately, so most of this is going to be kind of, I will say, Mexican food based primarily, directly south of the border. And what we'll do is we'll just look at kind of the various ways that induction works with doing these processes. And of course, what I would say is, try to translate these processes into whatever it is that you're doing. And if that helps generate some questions or, some realizations, then that's great. Over here, we have the unit that I was talking about with the temperature probe. And in the back here, I'm actually using this as a fryer. Can we go to the, there we go, perfect. So what we have here is a temperature probe in here. Now, of course, I'm not a big advocate of using a pot frying in a commercial setting, but if you have to do it, of course, you certainly can, and this is a way you could do it. I think a fryer is probably the safest way, but if you are doing something like a garnish or something like that, this is a great way to do it. It's also, what we're doing here is really just trying to show that we can maintain temperature and the recovery is quick. So whatever I put in here, it's not seeing that drop in temperature. And then in the front here, I'm going to be, now the unit is not on, but I just have my pans pre-set up. Here we have a unit that can either cook by temperature, just in the settings, or by power. I'm going to be using this unit primarily in its power setting, so more of like a saute situation. But as you can see here, it's pretty light. This unit is 5 kW for both hobs, and this one is 5 kW in the back and 3.5 kW in the front. I think that's a really important thing to note, because if you have 5 kW in the front, sometimes that can actually be too much power for your cooks. So it's something definitely to consider. You want to keep maybe that 5 kW in the back for production, and in the front you can use a little bit less power if you're doing like just general saute work. So over here, what we have is it's a well. So you'd often see this as you're set up in a on your line. But what's kind of interesting about this setup is you can see here I have butter in the back. My butter is not melted. Now obviously I have eggs, and I have used my time temperature logging, my 4 hours and all that good stuff. But you can see that they're not warm. If I was using a standard well, this could be quite a problem. But I'm also able to keep things, warm up front. I'm able to do that by temperature, and then I can even have a sauce here sitting right next to my eggs or whatever that might be. Now, I'm not saying that you can always do, I'm not advocating that this is how you always keep your setup. What I'm doing here is just trying to illustrate the differences. Here I actually have an induction griddle. This is a small griddle. That's kind of the, I think this is probably the best application for most induction griddles, in that it's small, it's light, but incredibly powerful. And we're not just talking about the temperature it can get to, the set point, but what we're talking about is how fast it can recover. This only requires a 30 amp plug, and its ability to recover is pretty quick. So that means if I'm using this for something like an action station or something like that, this is a really great way to be able to get a lot of firepower in a pretty small setting. Okay, so I'm going to do 3 different dishes, and I would invite people to have, if you have any questions, please ask them now. I can talk through them while we're doing some of the cooking. But I'm going to be doing kind of a huevos rancheros style, the way you're looking at the tortillas. I'm going to do some carnitas style tacos, and then some churros. So kind of just playing on that whole, like, you know, maybe 3 courses, brunchy or lunch type style menu. Okay, so first up, what I'm going to do is I'm going to start I'm actually going to start my tortillas for my huevos rancheros first. I'm going to use a little bit of oil here. I've been holding these tortillas. I've been practicing making homemade tortillas here, so we'll see how they work out. This is not something I've actually made a lot of. You know, sometimes there's just those situations where you don't get to make a lot of things. Like that one didn't hold well. What I did was I actually made them. I pressed them yesterday and then steamed them in the combi, and I'm testing to see if I can, you know, set them and then hold them and then pick them up a little bit faster later and still get, you know, capture as much of that fresh flavor as possible. So here I'm going to cook a few eggs. You know what I'm actually going to do? I'm going to put in the back where I have a little bit of a race. I'm going to take my, I had a little pot. Where did it go? I had a little pot of water. Anybody see my pot of water? I'm going to put a little, I'm going to go grab just a little bit of water. I don't know. Oh, here it is. And this is about, what's this room? Probably about 70 degrees right now. So this water's been sitting here for a little while. So it's about 70 degrees. It's not hot, I promise. I didn't preheat it. So, but it's a great way, I think, to show just how fast the unit can be. So as I'm doing my eggs, I'll preheat this water in the back. So we just got it started, and I can already see some bubbles in the back there. So it's about 2.5 cups of water. And then up front here, I'm going to cook some eggs. So I'm going to do like a basted egg style. Here, I'll just do a little bit of butter in there because why not? Eggs love butter. So what's cool here is you watch. Okay, so I'm going to, normally I'd want to preheat the pan a little bit, but because it's so fast, I can actually get my butter in, get it moving around. You know, as you can see my water in the back here, it's already almost bubbling away. Now I'm going to drop my temperature pretty quick. I'm going to put it down to like 2. Now, as you can see there, the temperature, you know, I didn't scorch the butter. It actually it's pretty responsive. I'll do my 2 eggs here. Got a little shell in there. Okay. So look, my water is already boiling. I think that was probably what, 1 minute and 10 seconds? It's pretty fast, pretty impressive. And then what's neat is if I turn it down, you can see there it's basically off, on. I want to get it back up to boiling. Boom, right back up to boiling. So it's very, very fast. Put just a little bit of water in here. And as you can see, it's actually pretty gentle if I want it to be. So do this. I'm going to cover them over. And then I'm going to check on my tortilla here. I'm going to add a little bit of oil and get it. I like a little texture on them. So I'll let them get a little bit crispy. And then over here, I'm going to put start my carnitas. So I was able to hold it at a pretty pretty stable temperature. Right now I'm holding at 190. Now you can, of course, change that. It tops out at 190, but that's what I find to be kind of the sweet spot for holding a lot of the meats. Now you notice I put it in a cold pan again. Now normally I would use a little bit of lard, but I have all that being used for another batch at the moment. So I'll just use a little bit of fat for this one. Cover that. Check my eggs. So what's nice here is just going to turn them off, let them sit for a second. Check my tortillas. So pretty quick here. Now, if I was using this griddle in a similar application, like let's say I have a tortilleria or like a Mexican restaurant or something where I am doing a lot of fresh tortillas, this is a pretty reasonable way, I think, to be able to pick up a lot of tortillas pretty fast, get that color, and keep moving. I also have my ranchero sauce here. So what's nice about that is I have a very small amount here, but what's nice about that is I'm actually able to hold it pretty accurately. It doesn't scorch, doesn't burn. If I had it set up where I'm using a lot more, I could just transfer it into a warm pot if I had to. I'm just going to put a little bit down here on the bottom. I'll put my misshapen one on the bottom there. And then I'll add just a little bit more. Now again, I'm just here to trying to illustrate, how you would want to use these things. You can judge my huevos rancheros if you'd like. A little bit of salt in here as well. Even it out. I don't claim to be the aficionado. So do that, and then I have my eggs over here. And then what I'll do is do it'll slide, that's okay. And what huevos rancheros would be complete without the all-important cotija cheese and, of course, cilantro, right? We got to have all the goods on there. So I'll pop these guys out. I was trying to keep them cold so they wouldn't die. It's one of the most comfortable kitchens I've ever been in, but the cilantro still doesn't enjoy it too much. So what we have here is a little bit of cotija, and then we'll put just a couple pieces of, just a couple pieces of cilantro on there. And your hangover is cured. So our huevos rancheros. Now, what I want to talk about too here is, the versatility of using the induction as a fryer. I'm actually going to move this guy over here so you can see a little bit better. And what I have here are a few churros. What I did was I actually pre-piped the churros, and then I stuck them in a blast chiller and shock froze them. So, I can make fresh churros. And, I can still handle them pretty easily. I don't have to have like a bunch of dough and try and pipe it into the oil, things like that. So again, it's all about being able to work as effectively as possible. My carnitas are working. Do we have any questions? Do we have anything come through? Not as of yet, okay. What I'll do here is see if I have a little backup of these guys just in case this didn't work out, but what I'll do, I'll grab my backup. Always got to have your backup. There we are. And then what I've done here is I've actually taken the this combi over here, just in case this happened, right? So what ended up happening was I tried to hold them for a little too long and they just got a little bit dry. Things happen. So what I'm going to do is I have a combi oven over here that I already have preset to use as a steamer. Whew. I'll throw them in there for just a second. Let them get nice and soft. Check my my churros. And as you can see here, what we're looking at is, we didn't see a drop in that temperature. They're able just to keep on going. And that's a really critical thing, especially if you're talking about, electric resistance or gas ranges where you're having to manually control that temperature all the time. That can be really tough. Whereas with this type of situation, I can set it and forget it. If I was making stocks or I'm making sauces, I can easily just put that probe in, set the temperature, and then of course, as that volume goes down, I don't have issues with it scorching or burning or anything like that. So I'll grab my soft tortillas here. Check my carnitas. Got to get all that crispy goodness. And as you can see here, I'm not getting a lot of burning on the sides, right? So because the heat is focused on the bottom, I can essentially just set it, forget it, know what surface is going to be making my crispiness and just go from there. And I can trust it. And then over here I have my tortillas. I'll get a little bit more color on those. There we go. My churros are working. As you can see, they're actually cooking pretty consistently and pretty quickly, right? I can watch my temperature here. It's telling me it's at 350 degrees. It hasn't really changed. Give these a quick flip. And I'm just using the lids to keep them nice and flat on there. It's not much weight. So I think that carnitas are pretty close. This out of the way. Give it a final season here. And of course, I just want to stir it around really quick. Of course, we always taste our food, right? It's okay. It's just me in here. So I'm not afraid of my own. I'm not afraid of my own cooties. Of course, I would have a tasting spoon set up if that was the case. And as you can see here, pretty even in heating. And if I need to turn it off, bam, just that easy. It's already off. It's not going to continue cooking. There's no heat bleeding in from the the range top or the electric resistance. It's basically done. So I'm going to I'll just do two tacos for this one. So we got our one, our two. We'll do three. Why not? 1, 2, 3. Oh, that's another thing. See, of course I have it. Actually don't need it because there's no convective heat touching the handle. So another thing you can be cutting down on potentially is your linen bills, because you don't need a bunch of towels to go through to keep grabbing handles that keep burning everybody because they're just so hot. So I'll put this guy over here. I know I'm using tweezers for carnitas, but for television sometimes you gotta. So here we go. Get a little bit more on there. Some other technologies I think are important to note here also are things like vacuum sealers. So I'm just going to do a little bit of crema on top here. I'm sure everybody's got an opinion, but this is how I'm doing it. So, and if you have any better ideas, of course, I always want to know. You have a recipe that I should try, or you think it works better, I am all about it. So what I did here was I actually, to cut down on time or just make things more stable, what I did was I compressed cabbage, some serranos, red onion, and cilantro and lime juice. And what that does is now I don't have to hold any of these things in water. I can pre-cut them and infuse them. So I put a little bit of salt in there, of course, too, so they're already pre-seasoned. And I'm able to control that flavor. And this actually will last quite a long time. So I can even use it for these radishes. I don't have to hold my radishes in water. I can pre-cut them. They'll maintain their texture. And I'm now able to, again, stabilize my production schedules, but still be able to maintain the same standard of quality that I had originally, that I wanted, right, for my guests. And then of course, I'll do a little bit of cotija over the top. And we're good. And another way I did that here, I was going to use this for the huevos rancheros, was I actually sealed some just some avocado in a bag, just to see how it would work out. Basically made it like a little piping bag. You could do it as little dots, I guess, or however. I cut the hole a little bit too small, but you get the idea. You could blend that really smoothly into a puree and do it that way. And then finally here we have our churros, which look like they're about ready. And what I did was here, I made a little bit of a chocolate sauce. It's kind of like a Mexican style chocolate sauce. There's like cinnamon in there. I basically made like crema creme anglaise with chocolate creme anglaise. And it's really nice to do on the induction because I don't need a double boiler. So I'm going to pull my churros out here. Got my sugar and cinnamon all pre-mixed up. And then voila, right, we got ourselves a little brunchy brunch meal. Right, well, might as well just stick them all in there, why not? So one lucky guest. And then my wife's a pastry chef. She always makes the mess with me, but I'm just gonna put a little powdered sugar on there. She doesn't like doing that. So as you can see here, we made 3 dishes, relatively simple dishes, but I can say that it was pretty fast. It was pretty easy. It didn't require a lot of, it didn't require a lot of like towels or, and it's very clean. If I need to come over here and clean up before chef comes along and gives me grief, cleanup is pretty simple. I just have one towel here. This towel is not even wet. It's actually just dry. It was my spare hand towel. And if you can do an overhead shot there, you can see that, everything's pretty clean. I don't really have a lot of, debris on the range tops. This thing over here is pretty easy to wipe down. I'm able to maintain my temperature. My butter's still soft, and my eggs are doing just fine in the back. So pretty neat. What we can do is let's go move on here. We have a few more slides. I think Jennifer had some more things to share, and then we can wrap up with any questions that you might have. No, not yet. Okay. So Jennifer, I'm going to pass it over to you and let you do your thing, and I'll control the slides for you.
Thank you so much, Chef Mark, and you have made me very hungry. So we are close to lunchtime. So I want to introduce everybody to AMP's kitchen programs and incentives. Next slide. Let's just click through the animation. I think there's like 3 clicks. Thank you. So Chef Mark showed us a couple of different pieces of equipment for your commercial kitchen. such as ovens, fryers, griddles, stove tops, and I don't know if we saw the steamers, but I think we did. And AMP provides rebates for several of these pieces of equipment, along with ice makers, refrigeration doors, and other holding cabinets. You can find more information about AMP's rebates for commercial kitchen equipment at our website. And we will be sharing this webinar on our website as well. So don't need to jot this down if you don't have a pen or paper ready. We will be sharing our links and this webinar. Next slide. Thank you. And so I'm assuming everybody will ask, how do I know what to do with my kitchen? And so we are offering free commercial kitchen audits to qualifying customers. In these audits, we'll show you how to save energy in your kitchen, learn about electrification opportunities, um, recommendations to save energy on specific operational needs, and other safety and fire hazard reduction methods. So if you are interested in a kitchen audit, please reach out to AMP in our contact by using our contact information in the next slide. Oh, sorry, the next slide. But for this one, this is our contact information. And let's go back to that previous slide, sorry. And just wanted to introduce everybody to some upcoming events in Alameda regarding electrification. On April 4th, there is a roadmap brainstorm for single family homeowners. And you can register at alameda.ca.gov. There will be another electrification 101 workshop at the Alameda Main Library on April 6th. Feel free to register at the Alameda City website. And then AMP will be offering you a Charging Your EV webinar on April 19th. This will be virtual and you can register through the link below. We will be emailing these links to you after this webinar if anybody is interested in registering. Thank you, Chef Mark. Next slide. And again, this is our contact information. My name again is Jennifer Shen, commercial program manager. You can also contact John Green. He is our commercial account manager. And I think that's it for me.
Okay, so just want to see if anybody has any questions before we wrap up. Looks like we're doing pretty good here. We're all ready to go. I'm sure everybody's hungry for lunch, so and working out. Did you guys happen to see any questions come through? Was there anything? We do have some. Oh, what would some of those questions be?
Chef Mark, this is Richard. I've been manning the questions, and we got some great questions related to residential induction. And does induction work for residential? And
Sure.
of course, the answer is yes. And when you get into residential, those safety benefits, the lower cooking temperature in the kitchen, and the air quality issues all matter that much more, because in a residence, you don't have professional cooks working the line, so it's much easier to get burned or set your house on fire. So the absence of flame is great. And of course, nobody wants to slave over a hot stove. So it's really nice to use induction cooking in residential. You can get small countertop units. In fact, the one that will be raffled off by Alameda Power is a countertop unit that could actually plug in to a regular 120 socket. But if you do want to go to a full-size induction residential range, you will need probably a 40 to 50 amp outlet at 220 volts, but that's exactly what you'd need if you were going to put in a regular electric resistance range. So they've made the induction ranges basically fit in the same slot as an old school electric resistance range. But there are various form factors. If you had, say, an ADU, you know, a mother-in-law house out in the back, you could get a little 2-hob drop-in induction residential range that will still run at a pretty low, maybe 20 amps. So there's lots of ways to work around this, but yes, induction works for commercial and it works great for residential, and so all great answers, great questions.
Great. So is that what do we have anything else, or looking pretty good?
Let me see. Oh, there was one more question, and it's, are there issues with induction for burner size compared to pot size? And Mark did mention that a little bit. If you have, say, a smaller countertop unit that has maybe a 6-inch diameter of that coil, and if you remember Mark showing you the coil, then if you put a 12-inch pot on top of that, and let's say you put some water in it, you'll see the water really boiling more intensely over that 6-inch diameter in the center. So it is best to try and match your pot size to the size of the induction coil if at all possible. And when you look at, say, a residential induction range, they actually draw, you know, big, medium, and small circles on the top of the range to help you understand how to match up your pot size to those specific coil sizes. Doesn't mean that you can't put a bigger pot. I put a pretty big omelet pan on top of a 6-inch coil on my countertop unit at home, and it'll work fine. You just kind of work around it a little bit. I move the pan a little bit to compensate, but it's still by far a much better omelet that I can make on my induction unit than I can make on my old Wedgwood gas range. And the eggs don't stick to the pan, and the handle stays cool. That was the other question. Some chef, somebody had noticed that you were able to pick up the pans, and you mentioned this too, without burning your hand, and that really comes down to the fact that you don't have all that waste heat going up the side of the pan and
Correct.
You know, making the handle hot, or like I say, when you're making your eggs, all that waste heat is what burns the eggs to the top of the pan and makes the pan so hard to clean out. So.
Just to touch one more time, a little bit on eggs. If anybody here has any experience working in kitchens where you do a lot of egg cookery, you know, a lot of times you'll see all the egg pans lined up along the range, and the flames are all kept very low and at a very at the ready stable temperature. The nice thing about doing something like this is because they're so fast and the temperature is so stable, you don't really have to leave them on. You could certainly have the pan set up and ready to go because that's just kind of how egg cookery usually works, but you can easily just have them off, and your preheat is so fast that, I mean, you just always set it to 1. You know what that temperature is going to be the right temperature for your egg cookery, and that's it. You know, you don't have to constantly, you know, or not constantly. Basically what you're doing is you're just adjusting those flames to always be at the ready, and you don't want to mess with them because that's like your temperature. But it's a very manual process where, because again, the induction is accurate and stable, you know, you just always have it at 1 or whatever that number or indication might be of your set point. You can just have the pans at the ready. You turn it on when you're ready to go, and within, I mean, you saw how fast the water boils. You know, eggs are cooked at a much lower temperature than that. You're ready to go really quickly, and you're not just using up gas or energy in general, just waiting to be at the ready, right? We actually do a lot of testing. A lot of our testing is actually based around what we call idling. Right? That's a big consumer of energy in kitchens, is really just things sitting at the ready, waiting to be used, waiting to do something, but they're consuming all the time. So because of that, we actually roll that into the efficiency numbers because it is such an important piece. So it is something to consider when you are looking at, you know, just having equipment idling or being at the ready, that there are a lot of great advantages to using induction over traditional technologies. So I just want to say thank you to all of you. Thank you to Alameda Municipal Power for supporting these programs. And we look forward to working with everybody out there again and helping you with any questions you might have. And you all have a great day. Thank you so much.